Hello, my name is Evgeni Gousev. I'm from Qualcomm AI Research, and I'm also one of the co-founders of tinyML Foundation. Before we start, let me use the technology and move where we were supposed to be this week. So now we are in the right place. So we are in Cyprus now. It's a beautiful place to be, especially in the summer. And with this, I would like to thank you, the organizers of this international symposium on VLSI, for putting together an interesting program and for inviting us to give a keynote presentation at the symposium. Unfortunately, this presentation and the whole symposium are virtual this year for the COVID reasons. But nevertheless, I hope that you will find this presentation and the video useful and informative. And if you have any questions, you can always contact me either on LinkedIn, or you can send me an email, and I'm going to show my email address on the next slide. So let's start. I'm going to go to work first, to my office, home office, and now I'm also going to share the presentation. We'll do it in the slide mode, and then we are ready to go. The title of my presentation today is Recent Progress on tinyML Technologies and Opportunities. And also I'm going to cover the always-on machine vision technology and the product we develop in Qualcomm. And you see my information on the bottom there, either my Qualcomm email or the tinyML.org email. And please send me an email or contact me if you have any questions after the presentation. The outline is as follows. First, I'm going to describe what tinyML is, why we are so excited about this new fast-growing field of machine learning, how tinyML is implemented, how it's done. I will talk a little bit about the tinyML Foundation. That's a non-profit organization we organized to accelerate tinyML technology development and ecosystem development globally. And this will be followed by some examples and applications. And that's really interesting because that's where tinyML shines. You're going to see so many different opportunities there. Basically, in every place we use sensing and processing, tinyML can be used. And our vision in tinyML is really to see a new world with trillion of connected devices that sense information and connect information and analyze information at the very edge. And that's basically the beauty of tinyML. And then in the second half, I will talk about the always-on computer vision product and technology that my team and I are developing and commercializing here in Qualcomm. So what is tinyML? So we enjoy living, actually let me start the laser. So you should be able to see the laser here. So we all enjoy living in the physical world, and the physical world is analog by definition. You see a lot of analog signals, analog creatures like my dog here, and yet we are increasingly living in the digital world. And the fact that this conference is VLSI Symposium is virtual this year, that's a testimony that kind of these two worlds are really connected, and we live more and more in the digital world. So these two worlds are connected through this device called transducer, which is typically consists of a sensor that senses analog information from the ambient, and analog information can be either image, camera, or sound, audio, or vibration from the IMU, or chemical sensing from the environment, and so on. And then it converts this information into digital through analog digital converters. And then you have some kind of processor, microcontroller processing unit here that analyzes information. And what happens today, then we have this, this digital information goes to the next level. And the next level is either Edge AI or Cloud AI, where the analytics takes place. And it works okay. However, this type of approach today has a lot of deficiencies. So number one, it's this type of approach is extremely energy inefficient. And this is simply because we're taking this analog information from here, and before it goes to the cloud, there's a lot of kind of steps are involved, and these steps are energy consuming, especially the transmission of the data, and because we have a lot of ones and zeros here, and especially if the information is sparse, we're kind of wasting a lot of energy by doing so. So that's one. Second is, so this type of approach has privacy issues, because what happens here during data transmission from the transducer type of device to the cloud, this information can be taken or stolen, and it can be used for whatever other reasons you don't want to be used, and that's a problem. Number three is because, again, we have this transmission questions, a problem. There are latency issues, and last but not least, if the network is down here, you cannot really transmit the data to the cloud, and you have reliability issues. So again, so the traditional AI today works okay or works fine, but it has several issues that needs to be taken care of. And that's where tinyML comes to play. So the tinyML is sits here, so it sits right at the boundary of the physical world and the digital world. And tiny machine learning enables machine intelligence right next to the physical world. And physically, it's kind of part of this type of device, sensor, analog to digital converter, and NPU. And by the way, this tiny machine learning can happen either in analog, in the digital domain here, or it can also take place in an analog domain. There are some companies who develop machine learning approaches in the analog domain. So you can do either way, depending on what you're trying to do. And what tinyML does, it solves the energy problem, because you're not transmitting tons of data, because the analytics happens right at the boundary of the physical and the digital world. So the output of this device is not raw data anymore. It's digested metadata, and typically it's just like much less in terms of bits. So you see less ones and zeros there, and it's private by design because we don't transmit tons of data. The latency is very good, and we're not relying on the network to be able to do the analytics here. So it has no connectivity issues. Again, tinyML is a very powerful approach, very powerful tool, very powerful technology, or a combination of technology that allows to connect the physical and digital world and do analytics right at the boundary of these two worlds. Extremely powerful. To be able to do it, it's not a trivial task, because typically the small devices are heavily constrained. So constraint number one is energy. So at best, all of these devices, they have memory, but they have battery, but at best the capacity of these batteries are quite small, typically from tens to hundreds of milliamps hours. and the requirements that these batteries need to last, need to work for years. So these systems have to be very, very energy efficient. That's one. Second, usually these tiny devices, they have some kind of processor, either general purpose or a dedicated processor. But because of the energy constraints, these processors, they're not like a GPU type of processors. They are typically from tens to hundreds megahertz at most. Because of the size requirements, and that's the constraint number three, you don't have too much memory there. You have typically have less than 1 megabytes, often less than 100 kilobytes of memory. So, and as you know, current deep neural nets, they require a lot of memory to store weights and activations and so on. So they are way above like 1 or 10 megabytes and easily to get really good production quality accuracy. So in a tinyML devices, that's not the case. You're also constrained by the memory, and that's quite important for people to develop the network. They need to realize this. And because the vision there is that these devices are everywhere and plentiful, the cost has to be very low to enable massive deployment. So again, these four constraints are quite fundamental, and they require a lot of innovations to happen to really make a good tinyML product. So how do you define tinyML? So very broadly, we define tinyML as machine learning architectures, technology, tools, and approaches capable of performing on-device analytics, as I said earlier, for all kind of different sensing modalities, vision, audio, motion, chemical. But what is important, all this has to happen at very low power, typically like in a milliwatt or below type of power range, and targeting mostly battery operated devices. Again, the key here is this extremely low power and on-device analytics for all different type of modalities. Why are we so excited about tinyML? Well, the reason is very simple. So if we believe that data is a new oil or new electricity, as some people say it, and machine learning is a tool or is a way to produce this new oil. So if you look at where data sources are, it's about 1% of data sources lives on the cloud. And that's kind of where current ML happens. Not too much. Then we see more and more machine learning happens at the edge, but the edge has only 4% of the data available. Typically, it's like pictures, audios, people do clicks, likes, GPS location, and that's what is used to do machine learning on edge devices, and it's only 4% of the data. And by contrast, 95, like the majority of the data, 95% data is in the tinyML space, and that's kind of where you see real-time data in the real physical world. And this data comes from different sources, from small cameras, from infrared cameras, from motion detectors like IMUs, from microphones, from environmental sensors, from temperatures, from optical sensors, from health sensors, all kind of things there. So all this data coming from this small transducer type of devices, they go into tinyML where the analytics happens. And again, it includes 95%, it accounts for 95% of the data. So again, if you believe that the new oil is data, that's where the oil is, that's where the money is. It's all in tinyML, so a lot of opportunities there. And that's why I think we are very excited and very bullish about tinyML, because it's a massive opportunity in all verticals where machine intelligence meets a real world. So it's in the health applications, it's in the AR type of applications, smart home type of applications. It's in the drone type of application. It's in the security camera type of application. It's industrial IoT. So tons of examples, smart city type of applications. So everywhere where you have a sensor, and if you need to do some kind of analytics on this sensor, that's where tinyML comes and it plays a major role there. And that's why we are so excited about this field. It just it's going to be everywhere, and we see that it's already kind of in many places. So our vision is because of this, we see a new world with trillions of connected devices. They all have on-device analytics, and it's all enabled and powered by tinyML. It will offer us a better and sustainable environment to live for all of us, because it will create a better and better, more energy efficient world. That's what it is today. So with this type of vision, we as I mentioned earlier, we started a tinyML Foundation, and this foundation is growing very rapidly. The mission of this organization is really to help and to promote this ecosystem growth worldwide, including software, hardware, application, and user type of people who really who are involved in tinyML and passionate about tinyML, and who are going to take this to solve big real world problems. So today it's like actually over 3,000 people in like many countries worldwide, and it's growing really fast. You can visit this website on the meetups to see the real-time growth of this community. To be able to do it, just kind of to give you a little bit of a snapshot what we do as the tinyML Foundation, as the community. There are several events, 3 events during the year. We have a summit typically in March timeframe. Next one is going to be in March 20 to 24th in California. We had 2 summits before, also in the Bay Area. We're going to have tinyML Asia event in the fall. It looks like this year it's also going to be virtual, unfortunately, but this event is going to be happening. And we were planning to have tinyML European, Middle East, Africa event also in Cyprus this year, in conjunction or co-located with the International Symposium on VLSI. And unfortunately, we didn't want to do it virtual. This event got moved to next year. So there are these global events. We're doing meetups. There are 23 groups in 17 countries and growing very fast. There are bi-weekly talks given by companies and academic institutions worldwide there. And then this information goes openly on the YouTube channel, just again to promote this global ecosystem. And it's a very diverse community. As I said, it includes experts, newcomers, academic, industrial, end users, software, hardware, system type of people. All they come together really to drive this very exciting field of tinyML. And if you're interested in getting involved, please visit the website tinyml.org. You're going to see all this information there, and again, it's a very exciting field and very exciting time to be part of it. Okay, let's talk a little bit about how tinyML is implemented. I think from our experience in Qualcomm and also in the whole community, I think what we see and what we learn is the key here is to make sure the whole system is optimized and designed holistically. So you need to design hardware, system, software all together as one piece, because that's the only way to have extremely efficient, highly integrated, this small technology, small form factor type of technology that is going to be doing the job it's supposed to be doing, which is on-device analytics always on type of fashion for many years at extreme energy efficient. And to be able to do it, you need to design things holistically, as I said, but also you need to optimize and do extreme optimization and innovation in all of these three areas. So that's the key. Again, that's our experience in Qualcomm, and that's what we also see by talking to our colleagues in the academia and also in the industry. Next, I'm going to make a statement, which is a very strong statement, that tinyML, although many people don't know about it yet, I think it's kind of gaining momentum very fast. But the statement I'm going to make is that tinyML is good enough now, the way it is now. If you look at all these three different areas, in the hardware area, we see a lot of companies, or many companies, who develop and commercialize dedicated hardware accelerators for tinyML. Most of them are in digital, some, as I mentioned earlier, in the analog domain. In terms of algorithms, we see a lot of tools and techniques and architecture search type of techniques where to be able to solve a problem and do your use case, you can use a lot of tricks or approaches like quantization, compression, pruning, and as a result, you can get smaller models around tens of kilobytes. And as you remember before, that's kind of as much memory footprint you have on these small embedded devices. So I think these models are already good enough for initial deployment. As a result, we see some initial tinyML applications. We'll talk about them in 5 minutes or so. And all these things are working fine. And I think at the same time, we see more and more innovations happening in all of these areas. And I think because of this, we expect there will be more enhancements coming in the near future. For example, in the hardware area, there are like approaches like compute in memory, analog compute, neuromorphic compute. So this type of technology are going to drive power efficiency by another maybe a 10x or 100x compared to the dedicated hardware accelerators. Obviously, depending on the workload, what needs to be done there. In the algorithmic area, there are novel algorithms, there are novel networks, neural architecture search, NAS tools have become more and more popular both in academia and in the industry. So this field is really growing really fast. So I think as a result, we expect that soon we will be able to see models with the memory requirements on the order of like tens of kilobytes. And these models will be quite accurate to be able to run, to be able to deliver the performance for specific workload. And as a result, this is going to drive a lot of value creation, more applications in the whole ecosystem. That is coming in the next probably 2-3 years or so. And on top of this, we see more and more foundational technologies, innovations happen in areas like ultra-low power sensors, novel memory type of technologies, 3D stacking type of technologies, energy scavenging, ultra-low power radios, and so on. So I think all these things connected, like in a very good, healthy ecosystem, again, is going to enable a lot of value creation and revenue creation enabled by tinyML. Again, remember, tinyML is all about digesting and collecting data from the physical world, and data is new oil. So that's why, again, we are very excited about this opportunity. We're very excited about all the innovations that happen in this area. And as I say, the tinyML is good enough now, and it's going to get better and better as more and more people and companies will work on this. Let me share some examples. First example is going to be voice, always-on voice. Always-on voice is becoming more and more popular. And like, for example, on Amazon Alexa type of devices or other type of devices. And this is just an example from one of the companies working in this area. This happened to be Sentient. What they do, they have a dedicated hardware, and dedicated hardware has few layers of neural net. I think that this particular chip NDP100 has 4 layers baked into the hardware. And as a result, you see that this device has extremely low power consumption. Always on power actually is in the hundreds of microwatts. It's a very, very impressive number. There are other companies. This is also a startup company, AON Devices from the Southern California, from the Irvine area. So what they do, also they have a dedicated architecture that allows to do training at a much smaller footprint and in terms of neural network weights, and that allows to have low power AI implementation. In this case, also on the order of 100 microamps or so, and that allows to run multiple models on this type of device. So again, always-on voice is coming, and tinyML is going to play a bigger role there, and there are already several companies, several products already on the market with tinyML voice applications. So next one, let's talk about MEMS sensors. So this slide I borrow from the CEO of Bosch Sensor Tech. As you know, Bosch Sensor Tech is a major player in the sensor world. I think they are #1 in the world. And this slide shows the software evolution from very basic software that enables kind of this sensor MEMS type of devices into the kind of the second wave until recently, where you can do some programmability in terms of microcontrollers. You can run some algorithms, you can run some sensor fusion there. But what is coming now from today on, it's really the HAI and sensor intelligence here. And what they highlight in their presentation is that software is becoming increasingly intelligent, enabling AI inside the sensor itself. That's the key. Sensor companies are looking at this as an opportunity to bring AI to the sensor world. And Bosch is shipping over like billion of type of devices a year, and you can imagine if each of these devices is going to have AI inside, enabled powered by tinyML, this is going to be extremely powerful in terms of applications and for end users. So what are they going to use it for? Again, this is from Stefan's presentation a few months back. Some examples here, you can use tinyML for environmental sensing. For example, in this case, this is a baby diaper. And if you use sensor type of devices like measuring raw temperature, pressure, humidity, and so on, you can get some useful information like, is this diaper clean, dirty, or wet type of thing. So this is, again, digital device, analog device. It's probably as analog as it gets. The diaper, and by using tinyML, you can get very useful information out of there. So another example, I think that is going to be probably more and more increasingly important in our kind of current world with a lot of environmental issues and the global warming and so on. How do you sense all this type of information in real time, in real world? In this particular case, it's a sensor that has temperature, pressure, humidity, airflow type of capabilities, and you can use tinyML, and by doing so, you can build very accurate climate models, you can do fire models, you can do early fire detection, risk evaluation. So the point here is you can use this tinyML to really solve big problems we have today, like in environment and in the world around us. And it's all, again, due to the fact that we can do machine intelligence and analytics at this very small type of device at extremely low power. It's, again, that's where the beauty of tinyML comes and the impact it's going to bring to the world. So next example is using IMUs, inertia measurement units, basically vibrations. So that came from tinyML. I borrowed it from Chris, obviously with his permission. So what the technology allows, you can attach, and I think it's shown here, you can attach accelerometer or gyro to a motor, and you can see by doing tinyML, you can do some predictive maintenance. You can see when this motor is about to fail, or are there any abnormalities in the behavior of this motor. And in the industrial applications, like let's say big plants or refineries or oil lines or whatever heavy machinery, this predictive maintenance is going to save a lot of money. And again, due to tinyML, that happens in real life, and it brings a lot of value to the end users there. Okay, so let's move on to the technology we developed in Qualcomm. So this is tinyML for Alwayson Vision. So what you see here is the product we have. So this tiny sensor, it's a camera. It's a very tiny camera. You can see there is a dime here. In fact, I have it here. It's kind of that's what it looks like in real life. This small device, and this is a picture. So this very small device, it's technically speaking, it's a camera. It collects information from the ambient, and then it does all the analytics on this device. So what it has under the hood, it's shown here. There is a lens, which is here. There is a sensor, which is a CMOS image sensor with very low power. And then we have a dedicated processor that does low power computation, but it also has several dedicated hardware blocks that allow to do this machine learning and computer vision in this very small form factor at extreme low power. We also have a dedicated memory there, which is a special design, low power memory. And we also have embedded power management unit as well, which is not shown there. So all this device end-to-end consumes less than 1 milliwatt of power, and this is extremely low power. So by comparison, if you do computer vision today, you have a regular camera and a processor. A regular camera, let's say HD, 720 HD or VGA or QVGA camera, consumes typically tens to hundreds of milliwatts. And then if you have a processor, depending on the efficiency of the processor, either CPU, GPU, you can get another probably tens or hundreds of milliwatts of power. So the end-to-end power today is hundreds of milliwatts to be able to do computer vision. So what we've accomplished in Qualcomm, and that's our key innovation and our pride, we've been able to get this power consumption to less than 1 milliwatt. And again, how we did it, as I mentioned earlier, the key here was really the holistic design. So the whole system, sensor, processor, algorithms, were all designed all together. So we have a very strong and very diverse team of people who are software, system, algorithm, hardware people, ASIC design people. We work together really to make this, and optics people for the lens, to make this technology happen. So because of this, it has a small size, and using CMOS technologies or silicon technology, size always translates into money, into the cost. So small size means low cost. What is important also here, and many customers I really appreciate this, this device, this camera, it doesn't send the image, it sends the metadata to the main processor. And this type of device, it can be configured for different use cases. The sensor itself is infrared compatible sensor, and I mentioned earlier, this device has low cost. Why we're so excited about this? Because this type of vision, low power vision or always on vision, can enable a lot of use cases in many verticals. And those are just some examples. In the smartphone case, it can do face-based auto wake or auto sleep, or it can trigger always on trigger for other use cases, like, for example, iris identification. Smartwatch type of application, it's also face-based ID or always on gestures. For tablet type of applications, you can do landscape, portrait mode, user orientation, or you can do gaze detection. VR is a very interesting application for always on vision, for low power vision, because this type of AR, VR devices are also very heavily constrained by the battery and also by the heat management there. So I think always on vision can be used there for like gaze tracking or 6 degrees of freedom visual odometric type of applications. It can be used in smart home type of application. My bird is getting excited. It can be used as an intelligent trigger for smart home applications, or it can be used as a standalone intelligent data sensor. Again, remember, we spoke before that data is a new oil, which is money. So by collecting data from the environment, you can build like heat maps of the building. Is the space occupied or not? And it can be done always in the privacy matter. So the privacy is a big important factor here, because we are not collecting images, we're just digesting and doing analytics on the device in real time. Again, tons of opportunities for vision in general. For humans, most of our kind of perception of the world comes through eyes. It's about like 90% of our world comes through eyes. So the vision is very important, and doing this at low power is really big fundamental advantage we've developed here in Qualcomm. Just to show you some of the examples, some of the use cases there for the always on vision. So you see bounded boxes there for different models we developed using this technology. You can do a body detection, either full body detection, far away. You can do 3/4 body detection, half body detection. You can do motion detection, change detection. I think one very useful, very powerful use case is face detection, and we can do it in different orientations there. This one shows gestures. We can do left, right, up, down type of gestures there. We can train the model to do different object detection. I think what we show here, the model inference model was trained to detect this type of logos. It can be actually even more complicated logos there. So this use case is a very powerful use case for retail applications. So we can use vision to do the shelf status, if the shelf is empty or full, or we can use this always on vision to look at the customer engagement, like the dwell time. And in this case, again, we do it without privacy taken into account there. So what we learn there is that doing computer vision using tinyML is quite different from doing more traditional computer vision. And those differences are quite fundamental. But the end result is very rewarding, because in the traditional approach, you can do it, but it consumes a lot of power. As I said earlier, typically tens to hundreds, sometimes even more milliwatts of power. In our approach, I think we are heavily constrained by this 1 milliwatt of power, and we have to innovate, and we had to innovate everywhere to be able to do it. For example, in our approach, image itself is not that important because all that's important is the information. In the traditional approach, image quality is #1 requirement there. In the traditional approach, color is a must in most cases. and also very good resolution of images in terms of bit depth. What we learned that in our case, monochrome type of sensor works quite well, and we don't really need to have bit depth there, like low bit depth, less than 8 bits is sufficient. In the traditional approach, getting good images by focusing, autofocus, bokeh, I think those are all important. In our low power machine vision approach, focus is okay, but it doesn't have to be very good because we can do a lot of things with the algorithms. We don't need to have high pixel count. Sensor resolution doesn't have to be high. Typically, VGA, QVGA, which is about 240 by 320 pixels, is good enough for most cases. And this is, again, in contrast to the traditional approaches where people usually use megapixel type of cameras. But again, you use megapixel cameras, it comes with the price, with the power price to do it. And in the traditional approach, sensor development and algorithm development, they're done separately. In our case, all of this is done, again, holistically together. So the sensor and the whole system and the hardware, they're all optimized together. The camera and the subject are always kind of positioned for the best image in the traditional approach. And for us, we can take images in really challenging light scenarios and very low light scenarios, and it works just fine. I think for us, when we do inference, it's more important compared to the traditional approach, where we need to have a good balance between the training and in the inference time. I think what is important for us to make sure we design the algorithms and the whole system with memory and power constraints in mind. That's kind of number one. And typically in the traditional approaches, people build their models based on what is available today. If GPU is available, then they use GPU, for example. And typically those traditional approaches are frame-based. And I think for us, I mean, we all care about events, like what happens in the scene. So I think that the point here that you really, I mean, in all these areas, we need to count every single penny, and you need to do savings everywhere. But again, the end result, we have a huge payoff, because compared to hundreds of milliwatts, we are a factor of 100 less here. We are like 1 milliwatt type. To be able to do it, I think we use like a system approach to always on computer vision. We favor algorithms that are adaptive. We typically do compute in the areas, or computer vision in the areas where we see changes. We like to run lightweight algorithms first. We kind of prefer to do early exits in our layers. We favor algorithms and models that have content adaptive capabilities. We don't run algorithms when we don't see any information there. And we kind of trying to simplify models and everything according to the images. We run multiple scales, and that we found is more energy efficient than resizing images. And then we do optimization in all the areas like low power sensor, low power IOs. We move algorithms as much as possible to the hardware. And I think what is also very well known by now in the AI hardware world, that memory needs to be located close to the compute engine. I think that's also key. Again, the point here, you really need to optimize and look at the whole thing here holistically, system and hardware and software. So this is the first product I think we are very proud of. This product is already commercial. You can buy these devices on the market today. It's a QCC 1112 chipset. It's, as I said earlier, power consumption less than 1 milliwatt, and it's all inclusive: chip, sensor, power management, everything. It has a low power microcontroller. It has a dedicated engine for acceleration, embedded PMU, and we have a dedicated memory and dedicated acceleration for vision. So it's, again, all this done in this very small footprint, and it's extremely energy efficient tinyML system that enables a lot of use cases. To summarize, I think, I hope I've been able to get you excited about tinyML. I think tinyML is really a very fast growing field of machine learning at the very edge of the physical world at extreme energy efficiency, typically at milliwatt type of power. Why we are so excited about this? Because there are like tons of opportunities, because it's all about data mining and analytics for many use cases and verticals. To be able to implement it, again, the kind of number one and the most important lesson is the whole system, hardware system, software, they need to be co-designed at the extreme. And I think in our case, we use even special design for our devices to be able to reach this type of power. And when, I think the question is now, I think we see a lot of products, a lot of opportunities. I showed some of them in the example. There's a big community growing, as I said, 3,000 people there. And I think we're going to see a lot of interesting implementations of tinyML in coming years. It's really an exciting field. It's very interdisciplinary by nature, and it enables a lot of real world type of problems to be solved using these type of devices. Very excited to be part of this field, and thank you for your attention. And if you have any questions, as I said at the beginning, feel free to contact me either on LinkedIn or by email, and I'll be happy to answer them. Thank you, and thank you for your attention again.